You are not what you think you are. The three-dimensional world you've inhabited your entire life, the depth, the distance, the solid reality of everything around you, might be an elaborate projection, a cosmic illusion encoded on a distant two-dimensional surface, like a hologram emerging from a flat screen. This isn't science fiction. It's not philosophical speculation. It's a hypothesis emerging from the bleeding edge of theoretical physics, supported by mathematical frameworks that describe our universe with unsettling accuracy. In 1997, physicist Juan Maldacena published a paper that would shake the foundations of modern physics. His work suggested something extraordinary, that our universe, with all its depth and complexity, might be mathematically equivalent to information encoded on a distant boundary, like shadows on the wall of Plato's cave, except we are the shadows, and the cave wall is more real than we are. What if the three dimensions you experience are emergent properties? What if space itself is not fundamental, but rather a holographic projection of quantum information encoded elsewhere? The evidence spans from black hole thermodynamics to quantum entanglement experiments, from string theory to gravitational anomalies. Each discovery points toward the same impossible conclusion. Today, we journey through evidence that challenges everything you believe about the nature of reality itself. Prepare yourselves. We begin.
In 1974, Stephen Hawking made a discovery that would haunt physics for decades. Working from his office at Cambridge University, Hawking applied quantum mechanics to the curved space-time around black holes. What he found seemed impossible. Black holes aren't entirely black. They emit radiation, they evaporate, and when they do, they appear to destroy information forever, something the laws of quantum mechanics strictly forbid. This became known as the information paradox, and it represented a fundamental crisis in physics. Either quantum mechanics was wrong, or general relativity was wrong, or our understanding of reality itself required radical revision. But hidden within this paradox lay a clue about the nature of space itself. Jacob Bekenstein, a graduate student at Princeton, had discovered something peculiar about black holes in 1972. He found that a black hole's entropy, the measure of information it contains, is proportional not to its volume, as you'd expect, but to its surface area, specifically the surface area of its event horizon. Consider what this means. If you have a sphere 1 meter in radius, it contains a certain volume of space. Now imagine a black hole with an event horizon of that same size. According to Bekenstein, all the information that black hole contains is encoded on its two-dimensional surface, not distributed throughout its three-dimensional interior. The implications rattled physicists. Why would nature care about surface area rather than volume? It's as if the black hole is storing information on its boundary, like data written on a computer screen, rather than throughout its interior. This represented a complete violation of our intuitions about space. In our everyday experience, if you want to store more information, you need more volume, more hard drives, more books, more space. But black holes seem to follow different rules entirely.
In 1993, Dutch physicist Gerard 't Hooft proposed a radical solution. What if black holes weren't the exception? What if all regions of space follow this same principle? 't Hooft suggested that the maximum information contained in any region of space is determined not by the volume of that region, but by the area of its boundary. He called this the holographic principle, after holograms, those flat films that contain three-dimensional images. When you look at a hologram, you see depth that doesn't exist on the film itself. The three-dimensional image is encoded in the interference patterns on a two-dimensional surface. 't Hooft suggested the universe might work the same way.
Three-dimensional space might be a projection of information encoded on a distant two-dimensional boundary. Leonard Susskind at Stanford independently arrived at similar conclusions. Working through the mathematics of string theory and black hole physics, Susskind found the same pattern emerging. Information in three dimensions could be perfectly described by processes on a two-dimensional surface. But this raised a troubling question. If our three-dimensional universe is a holographic projection, where is the hologram? What surface contains the encoding? And more disturbing, are we ourselves part of the projection?
In 1997, Juan Maldacena, a young physicist at Harvard, published a paper that would become the most cited paper in high-energy physics history. Maldacena was working with string theory, the hypothesis that fundamental particles are actually tiny vibrating strings. He was studying a particular type of universe described by string theory, anti-de Sitter space, a universe with negative curvature, like a saddle shaped extending infinitely. What Maldacena discovered seemed impossible at first. He found that a gravitational theory in this curved three-dimensional space plus time was mathematically equivalent to a quantum theory without gravity, living on the two-dimensional boundary of that space. Let me make this concrete. Imagine a cylinder. Now imagine a three-dimensional universe existing within that cylinder, complete with gravity, matter, and all the complexity we observe. Maldacena proved that everything happening in that three-dimensional interior could be perfectly described by a quantum theory on the two-dimensional surface of the cylinder, the boundary that wraps around it. The interior universe and the boundary theory are different descriptions of the same reality, like how a photograph and its negative show the same image in different forms. These two descriptions are mathematically equivalent, a concept physicists call duality. This wasn't merely mathematical philosophy. Maldacena showed that specific calculations in the three-dimensional universe matched precisely with calculations in the two-dimensional boundary theory. Particle interactions, field dynamics, even the curvature of space-time itself could be translated perfectly between these two descriptions. The three-dimensional universe, with all its apparent depth and volume, was a holographic projection of the two-dimensional boundary. Physicists call this the ADS-CFT correspondence, anti-de Sitter space / conformal field theory correspondence. Within months of publication, dozens of research groups verified Maldacena's mathematics. The correspondence was real. But this discovery raised more questions than it answered. Maldacena's work described a specific type of universe, not our own. Our universe has positive curvature, not negative. It's expanding, not static. Could the holographic principle apply to our actual universe? The evidence suggests something far stranger than anyone predicted. In 2006, Shinsei Ryu and Tadashi Takayanagi discovered something remarkable while studying the ADS/CFT correspondence. They found a precise mathematical relationship between quantum entanglement, the strange connection between particles across space, and the geometry of space-time itself. Here's what makes this profound. Quantum entanglement is a purely quantum phenomenon that exists in the boundary theory, the two-dimensional surface. But Ryu and Takayanagi showed that the amount of entanglement between regions on the boundary corresponds exactly to the geometry, the actual shape and structure of space-time, in the three-dimensional interior. More entanglement on the boundary means more connected space-time in the interior. Less entanglement means more disconnected space-time. The two are mathematically identical. This led to a stunning realization. Space-time itself might be emergent. Rather than being fundamental,
the three-dimensional space we experience might arise from the pattern of quantum entanglement in the underlying two-dimensional theory. Mark van Ramsdonk at the University of British Columbia pushed this further in 2010. He showed that if you remove all quantum entanglement from the boundary theory, space-time in the interior completely falls apart. Space itself depends on quantum connections. Think about that. The distance between you and the screen you're watching this on, the depth of the room around you, the vastness of space itself, all of it might emerge from quantum entanglement, like a hologram projected from a flat surface. In 2012, physicists Ahmed Almheri, Donald Moroff, Joseph Pociński, and James Sully discovered a new crisis in black hole physics that deepened the holographic mystery. They found that if information is preserved in black hole evaporation, as holography suggests, then either the event horizon must be a wall of incredibly high energy radiation, a firewall that would incinerate anything crossing it, or quantum mechanics breaks down, or space-time itself is not fundamental. The third option pointed toward holography. If space-time is emergent from entanglement, then the interior of a black hole might not exist as a real three-dimensional region at all. The event horizon might be the only real surface, with the interior being a holographic description without independent existence. Leonard Susskind and Juan Maldacena proposed in 2013 that the paradox resolves if entanglement and space-time connectivity are the same thing, a concept they called ER equals EPR, connecting Einstein-Rosen bridges, wormholes, with Einstein-Podolsky-Rosen pairs, entangled particles. The research suggested that quantum entanglement and geometric connections through space are two descriptions of the same phenomenon. When particles are entangled, they're connected by a tiny wormhole, a tunnel through space-time itself. But in the holographic description, this tunnel doesn't have independent existence. It's just a way of describing the entanglement pattern on the boundary.
Direct evidence for holography is extraordinarily difficult to obtain. Our universe doesn't have an obvious boundary where information might be encoded, but physicists have found indirect signatures that support the holographic picture. In 2017, researchers at the University of Vienna and the Institute for Quantum Optics and Quantum Information created a quantum simulator to model holographic spacetime. They encoded information about a simple two-dimensional quantum system and showed that it produced dynamics mathematically equivalent to gravity in 3 dimensions. The experiment was limited, a tiny quantum system, not a real universe, but it demonstrated that the mathematical relationships predicted by holography actually work in physical systems. More provocatively, measurements of quantum entanglement in condensed matter systems show the same scaling relationships predicted by holography. In 2018, researchers at Harvard found that entanglement entropy in certain quantum materials follows the area law, the same surface area dependence that black holes show. The pattern appears throughout physics. Systems that should store information in volume instead store it on surfaces. 3-dimensional behavior emerges from 2-dimensional information. But this represents just one piece of a much larger puzzle hidden in the structure of spacetime itself.
In 2010, Erik Verlinde at the University of Amsterdam published a controversial paper arguing that gravity itself is not fundamental but emergent, a byproduct of entropy and information. Verlinde showed that Newton's law of gravitation could be derived from thermodynamic principles applied to holographic screens. Gravity, he argued, is an entropic force, like the force that makes a rubber band contract when heated. It emerges from the tendency of systems to maximize entropy. If the universe is holographic, then gravity in our three-dimensional world is a consequence of information dynamics on the two-dimensional boundary. Just as temperature emerges from molecular motion, it's not fundamental, but rather a statistical property. Gravity might emerge from information flow. This explains something puzzling: why gravity is so much weaker than other forces. Electromagnetism, the strong nuclear force and the weak nuclear force, are fundamental quantum forces, but gravity might be fundamentally different, an emergent phenomenon that only appears at large scales when vast amounts of information interact. The mathematics works. Verlinde's equations reproduce both Newtonian gravity and, with modifications, general relativity. But the implications are staggering. Space-time curvature, gravitational attraction, even the motion of planets might be holographic effects, projections from information encoded elsewhere.
Our universe is accelerating in its expansion, driven by something we call dark energy. This creates a cosmic horizon, a distance beyond which light will never reach us, no matter how long we wait. This horizon has a surface area, and according to the holographic principle, that surface area determines the maximum information content of the observable universe. In 2003, Thomas Banks and Willy Fischler showed that the holographic bound in our universe is set by the dark energy scale. The amount of dark energy determines the size of our cosmic horizon, which determines how much information the universe can contain. Here's where it gets strange. The holographic bound suggests our universe contains approximately 10 to the 123 bits of information. This seems like an enormous number, but it's finite. The universe has a maximum information content determined by the area of its horizon in units of the Planck length squared, roughly 10 to the 123 square Planck lengths. If our universe is holographic, then all the information defining every particle, every star, every galaxy, everything within our cosmic horizon is encoded on that horizon boundary. We exist as projections from that distant surface. Raphael Bauso at UC Berkeley extended this into the covariant entropy bound, showing that the holographic principle applies to general spacetimes with horizons. Any region of spacetime has a maximum information content determined by the area of light sheets passing through it. The evidence extends beyond mathematics into observable consequences. In 2008, Craig Hogan at the Fermilab proposed something remarkable. If space-time is holographic, it should exhibit quantum noise, random fluctuations, at incredibly small scales. Hogan calculated that if information is fundamentally encoded on a 2D surface and projected into 3D space, there should be tiny inconsistencies in measurements of position and time. Not because our instruments are imperfect, but because space-time itself is grainy at the Planck scale. To test this, Hogan built the holometer at Fermilab, a device using laser interferometry to measure space-time fluctuations. The experiment ran from 2014 to 2017, measuring correlations in laser light at scales near the Planck length, 10 to the minus 35 meters, billions of times smaller than an atomic nucleus. The holometer found no evidence of holographic noise at the predicted frequency. But this doesn't disprove holography. It constrains specific models of how holographic projection might work. The fundamental principle could still be correct, with the noise appearing at different scales or in different forms than Hogan predicted. More intriguingly, physicists have proposed that gravitational wave detectors like LIGO might eventually detect holographic noise. As these instruments become more sensitive, reaching toward quantum limits, they might reveal the granular nature of space-time itself.
The most remarkable discovery involves how holography connects to quantum information theory, suggesting that the universe isn't just described by mathematics, it might be made of information itself. The evidence extends beyond black holes and string theory into the realm of quantum computing and information processing.
The ADS-CFT correspondence provides explicit mathematics for how holography works. In the boundary theory, quantum fields evolve according to well-established rules of quantum mechanics. No gravity, no curvature, just quantum particles and forces. But when you translate these quantum dynamics through the correspondence, gravity automatically emerges in the interior. The curvature of space-time appears as a consequence of quantum interactions on the boundary. Here's a specific example. Imagine a quark-gluon plasma, the super-hot state of matter that existed microseconds after the Big Bang. Calculating how this plasma behaves using conventional methods is extraordinarily difficult. The strong nuclear force creates complex quantum entanglements that overwhelm even supercomputers. But using ADS-CFT, physicists at the relativistic heavy ion collider translated the problem into a gravitational calculation in higher dimensions. The quantum plasma on the boundary corresponds to a black hole in the interior. By calculating how that black hole behaves, they derived properties of the plasma with remarkable accuracy. Experiments measuring quark-gluon plasmas in particle colliders match the holographic predictions. The physics is different, heavy ion collisions versus black holes, but the mathematics describes them equivalently. This forces us to reconsider fundamental assumptions about what's real and what's description. Not all physicists accept the holographic principle's most radical implications. There are several interpretations of what holography means for reality. The strong interpretation, championed by Susskind and others, argues that the boundary theory is fundamental and the interior spacetime is emergent, a useful description but not independently real. We are literally holographic projections, information patterns on a distant surface. The weak interpretation treats holography as a mathematical duality, a useful computational tool that provides equivalent descriptions of the same reality. Both the boundary and interior are real, just viewed from different perspectives. Some physicists argue holography only applies to specific mathematical universes, like the anti-de Sitter spaces, where it's been proven. Our actual universe has different geometry, positive cosmological constant, expanding space. The holographic principle might not apply to physical reality. But researchers, including Gary Horowitz and Raphael Bosso, have extended holographic ideas to de Sitter space, universes like ours with positive curvature and accelerating expansion. The mathematics becomes more subtle, the boundary less obvious, but the principle appears to hold. Edward Witten at the Institute for Advanced Study has noted that even if our universe isn't exactly holographic, the principle reveals something deep about the relationship between quantum information and geometry. Information theoretic limits seem to constrain spacetime itself. Physicists at the Perimeter Institute, including Lee Smolin and Fotini Markopoulou, have developed related approaches where spacetime emerges from networks of quantum information, spin networks, or causal sets. Space is not fundamental, but arises from relationships between quantum states. All these approaches share a common thread. Three-dimensional space might not be the fundamental arena of reality. Something else underlies it: quantum information, entanglement patterns, computational processes from which space emerges. How do we test whether our universe is holographic? Several approaches are emerging. The Event Horizon Telescope,
which captured the first image of a black hole in 2019, continues refining observations of black hole event horizons. According to holography, all information that falls into a black hole remains encoded on its event horizon. Future observations might detect information-theoretic signatures in the radiation patterns around event horizons. Quantum computers offer another testing ground. Researchers at Google and IBM are simulating holographic dualities using quantum circuits. In 2022, a team at Caltech and Google created a quantum circuit that exhibited dynamics equivalent to a curved spacetime, a tiny holographic universe in a quantum processor. These simulations grow more sophisticated. By creating quantum systems that perfectly mirror holographic predictions, researchers test whether the mathematical relationships hold in physical reality. Gravitational wave astronomy presents another opportunity. The LIGO and Virgo detectors, now joined by Kagra in Japan, measure ripples in spacetime from colliding black holes and neutron stars. As these instruments improve, they might detect subtle effects predicted by holography, quantum correlations in gravitational waves, information-theoretic bounds on black hole mergers, or even the granular structure of spacetime itself. The European Space Agency's LISA mission, planned for the 2030s, will detect gravitational waves from space with unprecedented precision. Some physicists believe LISA could reveal holographic signatures in the vacuum structure of spacetime. Recent breakthroughs suggest quantum information theory and holography are converging toward a unified picture of reality. In 2019, researchers at Caltech and MIT proved that complexity, a measure from computer science describing how difficult a quantum state is to create, corresponds to the volume of space-time regions in holographic theories. As quantum systems become more complex on the boundary, the corresponding space-time volume grows in the interior. This suggests something profound. The evolution of space-time might be a computational process. The universe might be, in some sense, a quantum computer calculating itself. Brian Swingle at Brandeis University has developed quantum circuits that construct holographic spacetimes from quantum gates. His work shows that specific patterns of quantum entanglement naturally generate geometry. Space emerges from information processing. This connects to quantum error correction, the technique that protects quantum information from noise. In 2015, researchers discovered that the ADS/CFT correspondence has the same mathematical structure as quantum error correction codes. The holographic mapping acts like an error-correcting code, with the boundary being the encoded information and the interior being the protected quantum data. This means space-time itself might be quantum information protected by a cosmic error-correcting code. Gravity, geometry, and distance might emerge from the universe's way of protecting quantum information. If the holographic principle is correct, the implications for human understanding are staggering. First, locality, the principle that objects are only directly influenced by their immediate surroundings, might be an illusion. In the boundary theory, distant points in our three-dimensional space might be adjacent. What seems far apart to us might be neighboring in the fundamental description. This could explain quantum entanglement's spooky action at a distance. Entangled particles aren't mysteriously connected across space. They're nearby on the holographic boundary, and the distance we perceive is the illusion. Second, the arrow of time might emerge from information flow. In holographic theories, the direction we call future corresponds to increasing entanglement and complexity in the boundary theory. Time might not be fundamental, but rather an emergent property of how information organizes itself. Third, consciousness and observation take on new dimensions. If reality is fundamentally information theoretic, the process of observation, the way conscious beings extract information from quantum systems, might play a more fundamental role than classical physics suggests. Some researchers speculate that the holographic principle could help explain the measurement problem in quantum mechanics, why observation causes quantum systems to assume definite states. If the universe is holographic, observation might be the process of projecting boundary information into interior reality. These are speculations, but they're grounded in serious theoretical frameworks that continue to reveal unexpected connections between quantum information, gravity, and the structure of reality itself. The most profound implications emerge when we consider what holography suggests about the nature of existence.
If our universe is holographic, what does this mean for reality itself? Consider your experience right now. You perceive 3 dimensions of space: height, width, depth. You sense your position in this 3-dimensional world. Every object has volume, every distance has depth. But holography suggests this 3-dimensional experience might be a projection, no more fundamentally real than the 3-dimensional image in a hologram. The real information, the actual physical description of you, of this moment, of everything you experience, exists as patterns on a 2-dimensional surface at the boundary of the universe. You are not a 3-dimensional object. You are information encoded on a 2-dimensional surface, experiencing itself as 3-dimensional through the mathematics of projection. This isn't to say you're not real. The hologram is real. The information exists. The patterns are physical. The experience is genuine. But the 3-dimensional form in which you experience reality might be emergent, like how temperature emerges from molecular motion without being a property of individual molecules. Distance itself might be emergent. When you reach out and touch an object, that sense of traversing space, of your hand moving through 3 dimensions to make contact, might be a holographic projection of quantum information processing on the boundary. The holographic principle suggests a path toward reconciling quantum mechanics and general relativity, physics's 2 foundational theories that remain mathematically incompatible. In standard approaches, physicists try to quantize gravity, to make gravity behave like a quantum force. But holography suggests a different approach. Gravity isn't fundamental, so it doesn't need to be quantized. Instead, gravity emerges from quantum information dynamics. This is why quantum mechanics and general relativity seem incompatible. They're not both fundamental. Quantum mechanics describes the underlying reality, the boundary theory, the information patterns. General relativity describes the emergent space-time, the interior projection. Trying to combine them is like trying to combine the rules of thermodynamics with the laws of molecular motion. They're descriptions at different levels. Thermodynamics emerges from molecular behavior. It doesn't need to be separately fundamental. Similarly, space-time and gravity might emerge from quantum information. The holographic principle provides the mathematics showing exactly how this emergence works. This unification extends beyond physics. The holographic principle suggests that information, bits of data, quantum states, computational processes might be more fundamental than space, time, or matter. The universe might be better understood as an information processing system than as objects moving through space.
This resonates with developments in quantum computing, where researchers increasingly view physical systems in terms of quantum information and computational complexity rather than traditional mechanical properties.
Perhaps most mind-bending, there might be multiple valid holographic descriptions of the same universe. The ADS-CFT correspondence shows that a three-dimensional interior and a two-dimensional boundary are mathematically equivalent. But are there other boundaries? Other projections? Could the same universe be holographic from multiple perspectives? Some researchers suggest that every observer in the universe has their own holographic screen, their cosmic horizon. Your observable universe is a holographic projection from your horizon. My observable universe is a different projection from my horizon. These aren't contradictory, but complementary descriptions of the same underlying reality. This leads to profound questions about objectivity and perspective. Is there a single objective reality, or are there multiple equally valid holographic descriptions that depend on the observer? The mathematics suggests both might be true simultaneously. There's an underlying quantum information structure, the boundary theory, that's objective and unique. But the three-dimensional space-time we experience, the interior, can be described in multiple ways depending on the holographic screen we choose. You and I might be holographic projections from different boundaries, experiencing the same information structure as different three-dimensional realities. This connects to interpretations of quantum mechanics where observation creates reality. If space-time is emergent from quantum information and different observers have different holographic screens, then observation might literally construct the three-dimensional world each observer experiences. The universe isn't just stranger than we imagine. According to the holographic principle, it's stranger than we can directly perceive, because our perception itself is constrained by the mathematics of projection, like beings in a hologram trying to understand the film from which they're projected. We began with a simple question. What if the three-dimensional reality you experience is a projection from a two-dimensional surface? The evidence, from black hole thermodynamics to quantum entanglement, from string theory to quantum simulations, suggests this isn't mere speculation, but a fundamental insight into the nature of reality. The holographic principle tells us that information in three dimensions is equivalent to information on a two-dimensional boundary, that space-time and gravity emerge from quantum information dynamics, that the depth and distance we perceive might be projections from a flatter, more fundamental description. We've learned that quantum entanglement and geometric connections are the same phenomenon, that the universe has a maximum information content determined by its horizon, that consciousness and observation might play more fundamental roles than classical physics allows. But vast mysteries remain. We don't know if our actual universe is holographic. The mathematical proof exists only for specific theoretical spacetimes. We don't know where the boundary is or how the projection mechanism works. We don't know why nature would choose holographic encoding or what lies beyond the hologram. The current scientific consensus acknowledges holography's mathematical power while remaining cautious about its physical interpretation. The ADS-CFT correspondence is proven mathematics. The holographic principle applies definitively to black holes, but whether our everyday reality is fundamentally holographic remains an open question. What we do know is that reality is far stranger than our intuition suggests. Three-dimensional space might not be fundamental. Distance, locality, and even time might be emergent properties of deeper information-theoretic processes. As we build quantum computers that simulate holographic spacetimes, as gravitational wave detectors probe quantum limits, as observations of black holes become more precise, we move closer to understanding whether we live in a holographic universe.
The question isn't whether reality is strange. Reality is demonstrably strange. The question is whether we have the courage to follow the mathematics wherever it leads, even if it suggests that everything we think is fundamental is actually emergent, projected, holographic. You are information experiencing itself through the lens of three-dimensional projection, and somewhere, encoded on a distant two-dimensional boundary at the edge of your cosmic horizon, the data that defines this moment exists in a form we're only beginning to understand. The universe is vast. The mysteries are endless. The journey continues.